Hello, and welcome to the IMTS Spark virtual conference in the quality/inspection track entitled 3D Break Edge Measurements Improve Throughput, Quality, and Safety. I just want to clarify the topic is not breakage, but break edge. Break edge is a critical call out on many machine components, but there's no cage capable shop floor method for measuring break edge on most parts. Improperly broken edges can lead to critical failures, injuries to personnel during handling, or compromised performance of the part. The presentation offers a method to instantly quantify break edge on the shop floor and will provide real-world examples of its impact to various industries, including automotive, cutting tools, and aviation. We have two presenters today, Eric Novak, Senior Director of Research and Development at 4D Technology, and Kramer Lindell, an Applications Development Engineer at 4D Technology. Dr. Eric Novak has been Director of Business Development at 4D Technology since 2013. He has been developing instrumentation for precision metrology for more than 24 years in applications such as semiconductor, optics, aerospace, automotive, photovoltaics, and medical devices. Eric has received 7 international product awards, holds over a dozen patents, and has authored more than 60 publications and book chapters related to surface measurement and industrial process control. Kramer Lindell is an applications development engineer at 4D Technology, specializing in industrial measurement products. He has a bachelor's degree in physics from Winfield College. He's been with 4D for 3 years and previously worked in manufacturing, building the handheld 3D shop floor gauge. He's built and qualified more than 100 systems. Prior to 4D, Kramer trained people on scanning electron microscopes. I'm this session's moderator, Eric Brothers, senior editor of GIE Media's manufacturing group, which includes the publications, websites, social media, and digital offerings of aerospace manufacturing and design, today's medical developments, today's motor vehicles, and today's e-mobility. Each title focuses on design and manufacturing topics specific to its industry to give our readers insights to improve productivity, lower costs, and be successful. I'll be collecting your questions for Eric and Kramer to answer at the conclusion of their presentation. Attendees, please scroll over the bottom of your Zoom window to show the Q&A feature you can use to ask your questions. Eric and Kramer, the forum is yours.
All right. Thank you very much, Eric. So welcome, everyone, and thank you very much for attending today's talk. We're going to be a little bit differently than normal. We're going to try not to bore you with 45 minutes of slides. I'll have a few slides here to introduce the topic, and then we're actually going to turn it over to Kramer to perform some live measurements, allow you to see, how things work in action, and hopefully ask questions and get answers about real-world applications. So metrology, is actually a cost benefit to companies. It enables process control and does in fact reduce cost. There's a very common saying, mostly attributed to Peter Drucker, who's one of the fathers of modern manufacturing, that if you can't measure it, you can't improve it. While that's not always true, it does apply particularly well to small features that just can't be accurately estimated by eye or by traditional techniques. And, according to Quality Digest, poor quality control costs companies millions of dollars a year, according to their own survey of more than 100 different manufacturing organizations. Similarly, NIST has done numerous studies in the last couple decades, and their studies show an average economic benefit of good measurement to be almost 50 to 1. So today we're going to talk a lot about surface measurement, and just to be clear, surface measurement can encompass many different topics. There's micro roughness that might be measured with an AFM or 3D microscope or stylus system. There's waviness, just kind of mid-spatial frequency features that have to do with, ripple on a part. And then there's overall shape, such as you might measure with a CMM or stereoscope. Additionally, though, there's topics such as microgeometries, radii, chamfers, etc. And that's really going to be the main focus of our talk, obviously, today. And then similarly, also, along that same length and depth scales, you have defects, which can be scratches, burrs, nicks, and dents, which can impinge on, improperly broken edges or on chamfers. So we're going to cover a little bit about that as well. And edge geometry really does affect many critical characteristics of machine parts. So there's a safety concern, as burrs and sharp edges are actually a major source of personnel injury in manufacturing. Additionally, they can cause electrical shorts or cut wires if there's burrs that are in contact with critical surfaces or other components. There's a performance aspect to it where they can cause damage to other parts. Chamfer lengths can affect how flush fasteners are with a part. And edge brake is actually critical in a lot of fluid flow for fuel and airfoils in automotive, in aerospace, in other critical manufacturing industries. Edge geometry also affects the part longevity with, improper chamfers leading to fastener stress and failure, initiation of corrosion, structural integrity compromising, and cracking through unwanted stress. And then lastly, but not the least important at all, there's a big customer perception in terms of having properly machined parts. The human eye is really excellent at seeing small irregularities and terrible at estimating their size. So generally there's a nothing visible kind of spec on a lot of parts. And so you want to be able to measure things, get things under control so customers aren't going to reject parts they suspect or, in a commercial sense, so they're not going to have a poor feeling about part quality. Specifically, chamfered edges are critical to precision manufacturing, because of, how often they are implemented in critical geometries. So a chamfer is basically a straight line or planar transition between two surfaces of any arbitrary shape. It can be between a 90-degree corner, like in the upper right, between a flat and curved surface, like you see in the middle, or even between other random geometries. And chamfers generally are designed to prevent edge fractures, improve safety again by reducing sharpness, and ensure that burrs that can cause damage are removed from a given surface. Radiused edges have all of those same benefits, in terms of improving safety, lifetime, and perception, but also, again, they can be critical for air or fluid flow. They can affect sealing behavior, and they're very critical for cutting tools in terms of critical cutting surfaces have to have a proper radius in order to properly cut surfaces. And consequences of poor quality control really can be pretty severe. There's internal failure costs, and I won't go over all of those, but they include injuries, rework, reinspection, and part shortages, and external failure costs. And that's everything to do with the end customer. So repair and service and complaints, travel time, downtime as you try and fix manufacturing problems, warranty costs, and overall customer perception. And traditional shop floor inspection really is insufficient for edge brake and chamfer measurements. So most commonly, people are still using visual and hard gauges. They're highly operator dependent, they're not gauge capable, and generally you're only going to check a few points along a part. Next level of sophistication generally involves replication and then some cross-sectioning where you look at a shadow graph or maybe a 2D profiler. But there you have high material costs from the replication material. Measurements can take 30 or more minutes as the material has to dry, be cross-sectioned, then be analyzed. And these measurements are very sensitive to alignment. If you're not perfectly perpendicular to the feature you're testing, you're going to get cosine errors. And there's also some material dependence. Did the material truly conform to the surface you're trying to measure? And what that leads to is a lot of excess, rejection, and reworking. Because inspectors, especially in a lot of industries where the cost of failure is high, if they're in doubt, they're going to reject or rework it. And that can be literally millions of dollars a year in parts that don't need to be reworked, getting improperly sent back. Then there's 2D methods that are out there for looking at edge geometries, and they also have, their own limitations. There's a variety of laser line profilers where you project a single stripe across a part, They're generally limited to smaller parts. It's hard to get them, with large aerospace or into certain geometries. They're sensitive to particularly geometries in terms of the reflections that are coming off a part, and also sensitive to surface finish oftentimes, where very shiny surfaces or a difference between shiny and rough surface within the same field of view can give them problems. And any two-dimensional technique, again, is very sensitive to how it's aligned relative to the part. If you misalign it, you're going to get improper results because a radius will look larger or a chamfer will look longer. Then there's industrial stylus systems, similar types of limitations, smaller parts, single traces, very sensitive to alignment. And because of that, it can be a really long time to set up a part properly and ensure good results. And then lastly, CMMs are often used for edge geometries, but it's very expensive to tie up a CMM looking at small surface geometries. It's really not their strong suit. They're much better at looking at form and testing large geometries. And also they simply can't measure the finest edge radii. When you get down, below a few thou, they have a hard time. So 3D measurements really, solve a lot of these issues. If you have a handheld system, you can bring metrology right to the part, and Kramer's going to show you that. If it's optical, non-contact, non-destructive, but the real advantage is 3D data is insensitive to part misalignments. You can actually use the three-dimensional information to figure out how the part was oriented and then do all of your calculations independent of alignment. And you get a large field of view, large standoff, large depth range. All of those can make measurements extremely easy, as Kramer will show. Not going to dwell on specifics here, but this is actually the product we're going to be demonstrating today. The key things are you have about 1/3 of an inch field of view for the model we're going to show you, about 1/10 of a thou vertical resolution, and a range of more than 1/10 of an inch. And systems can be handheld, mounted in a microscope stand, or even automated on a robot for critical geometry measurements. And when you do edge break measurements, so here I'm showing you, and Kramer will show you live, this is our edge break standard, and he'll talk more about that. But you can actually get extremely accurate measurements. So, an R squared versus a certified standard of, better than 99.95%. Excellent linearity across a large range of parts, and very small standard deviations, less than 0.1% as you look at multiple trials. So polarized structured light, which is the technique we're using, or called PSL, here all of the measurements took just seconds per feature, whereas with optical comparators, again, you might be looking at up to 30 minutes to get a single trace across a part. Looking here at countersink hole measurements, where we're looking at chamfer lengths, again, excellent correlation. This was a known standard provided to us by a vendor across a very large range, more than a factor of 20 range between the smallest and the largest features. Again, good linearity, very small offset, less than 0.5 of a thou, and less than 5% of the time it took them to do the measurements using a stylus. And we're very insensitive with a three-dimensional technique to geometries. So if we think about misaligning our measurement system, so it's coming in at steep angles to a measurement part, or it's twisted, or as you see on the right, it's canted at another angle, you can actually be off in all cases by more than 30 degrees and actually have less than 1% error in your chamfer length, in your edge break radius, and things like that. And so that's, less than 1% then is very achievable by any operator. Just by eye, it's extremely easy to line things up within 15 degrees, even within 5 degrees. And, beyond that, the live video we provide will actually show part edges as being out of focus. So here's just an example of a measurement where, a feature is, canted at 45 degrees with respect to the field of view. And, we're able to measure, the chamfer length was designed to be 0.0566, and that's actually what it was measured despite being off by a huge angle. Whereas a 2D trace there would actually measure that if you looked at an X trace or a Y trace as 0.08 degree inches. So off by more than 25%. You can also use these systems to quantify, burrs and other things on edges. So here we see an improperly broken edge. Maybe someone forgot about it, but you can actually look at the raised material and find it automatically using your 3D data, quantify it, get lengths, widths, and heights. So you don't have to guess as to the severity of the defect. And when you're fixing it, you only need to remove as much material as the measurement tells you rather than over chamfering or over breaking an edge that can actually lead to thinness and compromise structural integrity. Here's a larger machining error, and this was, the part tore away prior to the end of the cutting process. So again, you can automatically find and quantify high and low points, fix only what actually needs fixing. And then kind of my last example in terms of, three-dimensional results is, these same systems can be used for things like pitting. So if you have corrosion or just pitting from the manufacturing process with a surface finish, you can actually measure an entire field of view at once and identify every single pit and sort them by height, weight, area, volume, width, length, or even density. And what does this translate into in terms of the real world? What it means is customers can reduce their rework significantly. Measurement time can go from days to hours or from hours to minutes. These are all real world examples. We've seen customers increase their yield by more than 20% by replacing visual inspection that had high failure rates with quantified results where an operator can actually measure right up to the specification limit with confidence. And bringing metrology to the part and having it be portable actually can allow some severe benefits, such as reducing disassembly and assembly time prior to inspection. And so in some cases, like with an airplane engine, that can actually reduce labor by a week. You can measure a component, you can see it's in spec, and only disassemble if it actually winds up being out of specification. And then again, due to the quickness of the technique, a lot of parts will have 20 or more edge break callouts on a single component, and we'll show you one here in a bit. So that might take many hours or even a couple days to measure. But if it's only a couple seconds per measurement, you can actually knock that off in a matter of minutes. So handheld 3D edge measurements do improve quality and save money. They provide comprehensive parameter calculations. You get results in seconds. The results are operator independent, and you're able to actually quantify additional features on surfaces as well, not just edge break or chamfer. And with that, I'm going to turn it over to Kramer, and we'll let him actually show you some real world results. Then we'll come back for questions. Thanks a lot, and take it away, Kramer.
All right, I'll go ahead and share my screen here. All right. Okay, there we go. Here's my setup, if you guys can see that okay. This is the 4D inspect we've been talking about. I have it here in the desktop setup configuration and a microscope stand. But like Eric was saying, this is made to be portable, handheld instrument. So a lot of people have this in a setup where it's in an Ergotron cart. You can have your all-in-one PC right here and move it to the part on a shop floor is the idea behind this instrument. This is a handheld surface gauge. So I have a focus aid right here that allows me to get to the correct focal length. I can put this down on any surface, click this button to take a measurement. Anything this blue LED right here reflects off of, I can get a surface map of that reflection, any surface that reflects off of, to get my a 3D surface map to get these small geometries we're talking about. So Eric had mentioned that we have a edge break standard. This is the edge break standard. I can show you guys that real quick. I know this isn't quite HD, but I can pull up a quick picture of that. Let you see that a little closer. We had this. This is EDM still. We had this custom made by Gauge Maker. And on this side, you can see the chamfer. On this left side here, a flat machined into the onto the edge to make two duller angles on this edge. So one part of this is a chamfer. The other side is a rounded edge at different sizes all along these the standard. So we had this made for our chamfer testing. We've done a significant amount of testing, as Eric alluded to. So I can go ahead and take some measurements on this standard here, just by putting up the inspec to the part itself and taking some measurements. So take a measurement. I'm going to put the inspec down, have that blue light reflect off of that surface. And when I'm in focus, I'll go ahead and click this button, just take a measurement. So I'll switch over to my live video here. So that left screen is my live video. And I'll go ahead and get this in focus. So when my surface is green, that means I am good to go. I'm in focus. When that happens, I can go ahead and click that button. And I'll be able to get a 3D surface map of that area. So there is my classic chamfer right there. I'll go ahead and go into the chamfer analysis tool. And what this does is identify all the data points that belong to this left side here, all the data points that belong to this right plane, and all data points that belong to that chamfer face there. And so that will analyze that, parse those out, rebuild even the material that has been removed from and machined away, making that chamfer. So these right lengths are and left lengths are certified to be about 8/1000ths of an inch. You can see this right length here. That's what we're getting. Turn my live video back on there. You can see the data points. This blue data points are belonging to this right plane. The pink ones belong to this left plane, and these red points belong to this chamfer face. So I'm also getting this chamfer length right here, some different parameters, which might be easiest to refer to this diagram right now. You can see I'm able to calculate with this 3D data the right length. So where these two planes would intersect, from where they stop, I can measure a right length, which is essentially the material that has been removed and machined away. This left length, the angles in between, and of course our chamfer length, which is an all important measurements. And I can do that fairly quickly. And as you can see, my lineup didn't really matter. I was able just to put the inspec down without really worrying too much of how I was aligned. And I think I did a fairly good job of aligning it, not too far off, but it's pretty simple to do. I was in focus, able to get within a few degrees, and I have, as Eric was saying, I have a good 30-degree window of being accurate there. And any tilt that I would have with this 3D data, that can be removed. And so unlike a 2D trace, a 2D stylus, or an optical comparator, I can remove that tilt using this 3D data and mathematically find the correct chamfer length and rebuild the structure that was there to get those right and left lengths. Yes, sir.
Can you actually maybe show folks a measurement that's not so
well
aligned?
Yeah, I'll try to mess it up a little more. Go back to my live video here, and I'll just show you guys what I'm doing here. So I can try to get a little askew. If I was just being sloppy and wanted to just come and take a quick measurement, I can put it down, go to my live video here, get it in focus. All right. All right, and once I'm green means go. So I'm not really doing a great job of lining it up there. Just as a demonstration. So here's my chamfer. I'll go and put that to the chamfer analysis, and I'll let that analyze that. Let it find these the data points that belong to each side. Let it remove that tilt using that 3D data.
So in this case, we're both twisted, and then the top of the chamfer was not lined up with the measurement instrument either, right?
Yeah, I tried to do a couple different. You can see I was a little more lined up than I thought I was, but I try to get this line a little bit, a few degrees off right there, but this is definitely clocked. And this is, you can see a little tilt on this axis as well. And this particular chamfer I was measuring is certified to 40 thousandths for this right length and left length here. So you can see I'm within under 1% there, under for air. So it's accurate within, I had to try to get this far off and it still stays accurate. So if you were in a situation where you couldn't exactly be orthogonal to the surface, if you're in a tight space, you could still measure chamfers accurately. So I can also show everybody how a rounded edge would work. A rounded edge is fairly similar to the chamfer in our analysis. Go back to my live video. I'll do the same thing with we're taking a measurement. On the other side here, we have rounded edges instead of the chamfers. I can put my inspec up to that surface, click this button when I'm in focus, and that blue LED will reflect back and give us our 3D surface map. So I'll get that into focus, like so. And when I'm ready, I'll take a measurement, click that button, and I get a 3D surface map of that rounded edge. All right, there we go. There's a rounded edge. I'll put that into the rounded edge analysis. And what rounded edge analysis is going to do is identify this left plane, this right plane, where that plane ends on either side, and where that curved area in the middle begins, which allows us to fit a best fit circle to the rounded area. And now we can find that edge break radius in the middle there. And so this edge break radius that I was measuring is certified to 40 thousandths of an inch. And you see it's identifying the curved area, the left and the right planes right there. And similar to the chamfer, we are removing any tilts, any alignment issues that I made, just taking it by hand right now. And we have different parameters we are calling out as well, or displaying here, that can be seen right here if anyone is interested. Again, that right length, that left length of the material that's been machined away, some different angles, and of course your edge break radius right there. I can go into that, giving you with you this presentation.
And this is a fairly large radius, but we've measured down to about 3,000, right?
Yep, that is correct. We have smaller radii if anyone's curious to see that. And I can take some measurements on some actual everyday parts instead of the standard. I have go to this, an automotive part here. I can take a measurement on. This has a many chamfered holes around here. I can take a measurement on. So go ahead and do that in a similar way to how I was doing these other ones. I can put the inspec up to a area of interest, just as similar to that edge break standard, and I can take a measurement when I'm ready, click that button. I'll go back to my 4D software here, back to my live video, and I will take a measurement of one of these chamfered holes. Okay. So I'll go ahead and take a measurement. See how that looks before I go into the chamfer analysis. And I'll crop an area of interest. So all these measurements, I can go back and analyze them later. So I have a queue of all the measurements I've taken in the past, recalculate them with a cropped area of interest if I wanted to. Here's a nice chamfer shape on this chamfered hole, and I can get a nice chamfer length right there pretty quickly. I don't have to worry about alignment issues. I can get a quick chamfer measurement on that hole pretty immediately, just easily with a handheld instrument that I could take to the part. And this particular part has many chamfered holes on it. So one way we tackle that problem is with automation. I can show you a quick video here of automation on these chamfered holes. This has dozens of edge break callouts on it. So taking all these measurements quickly with a UR3 robot, which is natively supported in our software, can help this process be sped up to fairly quickly. That's a quick little video that shows how quickly we can take all these measurements. All right, so that's some edge break analysis. I can go and show some defect analysis, which is what we do a lot with the inspec. We can look at some burrs. So I have a machined part here that wasn't machined very well, and I can take a look at one of these edges. That's fairly rough, and I'll use the microscope stand for this with this shape. I'll take that out. Put this in here. I'll just move this up and down until I'm in focus, and I'll go back ahead and switch back to my 3D software here, my 4D software, and get this in focus. When I'm green, I'm in focus. That looks good. I'm going to take a measurement of this surface and look at this edge here and see what we're seeing. Up some. All right. Okay. And now I could see this is my 3D view of the measurements of this surface. And I can see some edge artifacts right here. I can do a feature analysis, and I can look at heights. I'll go ahead and set my specifications to whatever I would wish them to be. 1 second, I'll move this for you guys. All right. I'll look for some measurements or some features that show up that are higher than a half an inch.
So in this case, nothing there was taller than a 1/2 tenth.
Yeah, exactly. Go ahead and make sure I measure from the surface of the material, and this should work here. So I set a reference so that we are measuring from this surface, our reference plane, and we can see this defect showing up here at about 2 thou is what we're seeing above this surface that I set as a 0 point. We are seeing this feature all across here. We can analyze this feature. It's showing its weighted height, its area, volume, length, width, everything you want to know about any of these features showing up. You want to see a 3D view of it. This is the burr on the edge of it. They're fairly large for a burr, and thought to the feature analysis. Everything we want to know about any of these can be displayed right here, just automatically. Any heights we wanted to see along the edge. And so Eric touched on that earlier, that this can also be used for any kind of heights, any depths. We can search for depth as well if there are any pitting, corrosion, things like that. And for edges, we can look at burrs like this and characterize those fairly quickly with our 3D measurement.
And again, Kramer, how many points are there within a given measurement?
There are about 4 million data points within our entire field of view. We're about 2K by 2K.
Okay.
All right.
And then what about if you have somewhere hard to reach where you can't come straight in with the inspect? So you have a tight space, or like if you're measuring inside of a tube or something, what would you do there?
Yeah, so I have have different attachments. So before we were using a focus aid to get us to the right focal distance. So when we're using the microscope stand, we didn't need this. We could do non-contact measurements just by getting to the right focus point using the microscope stand. So we're using the focus aid to get to that point using the handheld in handheld mode, sorry. And we have other attachments that go into the same slots. So if you want to get to a tight space, you can use a fold mirror and put that into the same space right there. So this fold mirror can bend this beam at a 90-degree angle. So if I had this is the part that I have right now that can be used to show this. I can get into a tight space right here that I couldn't normally get into. So I can take a measurement that's not within the line of sight. So I can get in here and take a measurement, look at any defects along the sides in between these blades right here. So I can take a measurement at a 90-degree angle. If I want to get in tight space, I can take a measurement in between. If I want to get into this this automotive part, if I want to get inside this the cylinder, I could use this this fold mirror to get inside the cylinder right here.
So you can do any of the radii call outs even within that tight space there.
Yes, I could. I could get in there.
All right. So yeah, no, thanks. That's a really good demonstration. And what are some types of parts? I know we were talking earlier. We don't have any gears available, right? But we've done measurements on them. We just don't have any in house right now, right?
Yeah, that's correct. We've done some radius measurements on and chamfer measurements on gears and hypoid gears for. I know there's one some automotive parts that we've done it on. We've done on many aviation parts.
And bearings and races, right?
Yeah, bearings and races. Yep. Pretty much anything that has an edge that needs to be measured and quantified, we can take a measurement on.
All right. Well, thanks.
Absolutely.
So I think that pretty much concludes the formal part of our presentation here. Where we have a little bit more time than originally scheduled for questions, but we wanted to leave more just in case people wanted to see some different measurements with the system, and if anyone wanted to ask more specific questions, so that we can go back to results. So I'm gonna share my screen back again as well with our contact information, and then
Well, I'll interject here and say thank you, Eric and Kramer, for explaining break edge and its importance to quality, productivity, and safety. I do have a couple of questions that come to mind. You talked about the polarized light. And that's ultraviolet. What's the importance of the wavelength, and what wavelength are you using, and what are its characteristics?
sure. So I can handle that. So we're using a blue LED. It's centered at about 450 nanometers. The only real reason we're using blue is because the blue LEDs are the brightest ones. They're the ones that are actually used beneath the phosphors for all of your home lighting. And so they get all the attention by industry. So there's nothing really magical about blue, but because it is an LED, the source has a lifetime, an MTBF of more than 100,000 hours. Now, where polarization comes in is what we're actually using as our measurement technique. Sometimes it's referred to as structured light. Other people will call it fringe projection. But we're kind of putting mathematically or optically generated stripes on a part, and then we look how they deviate in order to get the three-dimensional surface. Now, if you do that conventionally, you typically have to use multiple wavelengths or multiple colors or multiple types of stripes in order to get the three-dimensional result. And all of those mean you're taking multiple camera frames, and then you have to be steady between those. What we do is actually we use a custom camera where each pixel of the camera has a little polarizer in front of it, much like a color camera has little color filters in front of each pixel in order to give you a color image. With those multiple polarizers, we're able to get multiple images of the stripes all at once, and we're able to calculate the three-dimensional surface in a vibration immune way. So that's why Kramer can hold it by hand, or we can be on a robot, or we even have systems mounted in machining centers. So that's where polarization comes in. It's kind of 4D's trick, if you will. It's our claim to fame in how we can do vibration immune three-dimensional measurements, on the shop floor or in a production environment.
Okay, you almost intercepted my next question, was how easy is it to use inline, say with deburring operations? So you can mount them on a robot arm or have some repeatability in going in and measuring.
Yeah, so we're actually we have multiple systems in production worldwide already measuring different aerospace parts, even measuring some different cutting tools. And we do support, as Kramer mentioned earlier, the universal robot cobots natively, as in within our software, you can send the robot commands. If you have a different automation scheme or using FANUC or some other robot, we actually have a remote access software package where you can treat the system just like a probe and send it commands, load a recipe, take the measurement, give me back the edge break data or give me back the defect data all automatically. So we're pretty cognizant of what it takes to be in production, and we're fully supportive of those types of efforts.
So with cradle to grave tracking of things like turbine blades and things like that, do you have a way, like through Industry 4.0 or some other connection, to come up with a report that matches images of every blade or surface to a greater report that can be stored digitally somewhere as a digital twin?
Yeah, so when you take the data, you have multiple ways we can save it out. So you can actually save out the full 3D surface map, and that could be an XYZ point cloud that you save to the network so someone else can pull it in to do lifing measurements or CAD comparison or things like that. But in terms of the critical calculations, we'll actually output those as just commented limited files, .csv files, and those then can be led into any statistical process control or factory 4.0 system so they can be monitoring the results in real time. You can also just, for places that aren't quite at the industry, the 4.0 level, there's a button on screen that just will do a quick measurement report and save it off as either a PDF or a PNG file so that you have a digital record of the measurement, even if you're not uploading the data into the cloud for further analysis. So there's a few different ways you can handle that, but the computers are all Windows 10 64-bit Pro and fully networkable, and our software can store data however you need. In fact, one of our biggest customers has multiple systems, and we even wrote a little custom interface for them for their cloud interface so that they can be doing basically they have sites in, I don't know, at least 20 countries, and so they upload all of the data to a central server where they're doing tracking, as you say, in aerospace.
All right. How do changes in the surface reflection affect the measurement? Say you have a part you measure it, then you do some machining on it. It has an oil surface. Can you track that variation, or does that
So
change
if
the
there's
results
oil
between the
on,
two?
yeah, if there's oil on a surface, we might very well measure the oil. So we recommend to people just to quickly wipe them off so there's not, we are doing a measurement of the surface as seen by the instrument. So if you have a big, you know, oil droplet or a big, ball of dirt on it or something, we're going to measure that oil droplet or that dirt.
Okay, because it could fill
Generally,
in, it could fill in the pits or whatever. It changes the reflectivity and things like that. Is
it
that
could.
okay?
But now, in terms of what finishes we can handle, we can do anything from an ultra polished blade, which is mirror smooth, all the way to cast iron or black rubber, which are very dark and very, very rough. And even those can be in the same field of view. If uh, if you might have noticed when Kramer was doing the chamfer measurements, he got a nice green stripe along what the primary face he was measuring, but the rest of the live video looked kind of black. But even though it looked black and we had very low reflectivity, we still got three-dimensional data across all the surfaces. And so that kind of shows you we have an enormous dynamic range with the camera, so it can handle even within one field of view something very bright and very dark and still get results.
How about transparent media like optics and things like that? Do those throw it off?
Yeah, so a lot of transparent media can throw it off. Now we can measure certain features and have certain scratches and chips and things on glass. The real challenge there, though, is typically not so much our signal, but what the customer needs. So again, our noise floor on this instrument is on the several micrometer level, or somewhere around 100 millionths if you're thinking in inches, and glass and things like that typically are smooth to the nanometer scale. So typically people are trying to look for things that are beneath our noise floor. So even when we measure the surface, unless it has a really big chip out of it or something, we're not going to provide really the information people mostly want, which are, you know, nanometer scale scratches or sub-micrometer at least level features.
Okay, thanks. Kramer was using that standard block. Is that required for calibration in any way? If so, how often?
So that is actually not used for calibration. We do have an ISO certified calibration standard. We recommend it be used every 6 months. Although because there's no motor scanning mechanism or other motion involved in our measurements, basically you're going to see that the system will just say calibration verified and log that to our cal log file. And if it doesn't, likely the system's completely broken. And then because it's non-contact, that cal standard only has to be recertified every 5 years. And it has multiple steps on it, so you get both accuracy and linearity. The reason we developed that edge break standard is it's a bit of a mathematical stretch or mental stretch sometimes for people to think, how does a step height accuracy translate into an edge break radius accuracy? So we developed this as just a verification standard so that you can have it and people can have a golden standard where they can just periodically check if they want and make sure that, yeah, not only is the system under calibration on the step, but it is still measuring, or it is measuring my radius properly or my chamfer length properly, because those involve both lateral and vertical height scales or length scales.
Okay. I noticed that there's like a measuring stick or a focus aid. How much does the range affect results? Is there a sweet spot, plus or minus, that you have to hit every time to maintain accuracy?
Yeah, there is. So with this product, with the inspec that we were showing, the height range for things to be in focus is about 1/10 of an inch. So we use that stick just to get you there and make it really easy, to be at that right distance. Now we do have another product called the Inspec XL, which has twice the field of view, so a 2/3 inch field of view, and its depth range is actually a third of it, more than a third of an inch, so 9 millimeters. And so there you can be quite out of focus and actually get still good height results.
Is there any particular maintenance for the scanner? Obviously, you want to keep the optics clean and the light from getting dirty, things like that. Is there anything beyond the obvious?
There isn't. In fact, it's fully sealed with an IP rating of 5.3, so it's dust immune, also immune to even light, oil, and water spray won't affect it. The end face is made of Gorilla Glass, so if you get it dirty or smeared, just use Windex and a paper towel, nothing fancy to clean it, and it's all fully sealed, so there's no user maintenance. In fact, our biggest issue, honestly, has been sometimes the Ethernet cables aren't even when you get industrial ones, they're not the highest quality. But in terms of anything with the instrument, there's nothing the user will do. There's no preventive maintenance or grease or oil or anything else that will have to be done.
Good to know. Another question, can you stitch those scans? Obviously, the nice edge, and you're doing a very thin strip. Is there a way to sort of put all that together to get a big picture?
So we have worked with customers using robots where we know exactly the orientation of the system, and then that becomes quite easy to stitch together. So someone was looking at the edge of turbine blades and the shape, and our system wasn't fast enough for the shape, so they did a very rough shape measurement with another tool like a stereoscope, and then they added on the high resolution edge data from our instrument. In general, it's hard for us to stitch data together because, well, at least when it's handheld, because with 6 degrees of freedom, unless you have a big pit or scratch or something that overlaps between fields of view, it's hard for us to know how one image relates to another unless it's on a robot
Okay.
that's actually tracking that. So it's
Okay.
something that for automation is something we support. For handheld, we're looking at what we can do to make it better. We have some engineering prototype version of that, but nothing released to date.
So if you needed a scan of a complete gear with every tooth, you could have an indexing system and just kind of have a slideshow, I guess, to see if there are any variations between those.
Yeah, exactly. Typically, we would tell people 100% coverage. And that's also true because with 4 million data points per measurement, it doesn't take a lot of measurements before even with a computer with high amounts of RAM and processing speed gets bogged down, right? When you have you know maybe hundreds of millions of data points, it's so much denser data than you would get from a CMM or most other things that generally I recommend people do 100% coverage. Don't do stitching. And there's also issues with stitching when you're looking at microscale features that if there's any kind of error or any kind of shape in the shape in the part becomes difficult to remove as you go over more and more of the part. And so it's harder to pick out those defects automatically with software.
Sounds like something for artificial intelligence to go sorting through data to find the exceptions.
Absolutely.
Okay. Can you measure chamfers, bolt holes, or other curved surfaces or features?
Yeah, we measure into corners. We've measured spherical parts. We measure, I mean, just in aerospace, we're all over measuring anything from vacuum tubes to tiny little gears and things. So part shape, again, because of our fairly substantial depth of focus, we can handle parts of various shapes. And then if you saw when Kramer was measuring the automotive part, even when things go out of focus within the field of view, you can draw a region of interest just around the specific features you're most interested in and generally get really good data even on a very complex part, which fundamentally, exceeds our depth of focus.
Kramer experimented a little bit with the orientation of the system or the part or to the surface. How sensitive are the chamfer and radius measurements to that orientation?
Hey, Kramer, you've done all the studies on that. Do you want to chime in on that one?
Yeah. So depends on which chamfer or rounded edge you're looking at. Rounded edge is a little bit more of a complicated calculation. So those ones will be a little bit tighter on your tolerances, but all of them you can deviate in every axis up to 15 degrees each way. So you can have a 30-degree window for rounded edge rotating in Z, X, and Y. So it's fairly forgiving and allows you to pick up all the data you need and put that together and get an accurate calculation.
And again, when we're talking about accuracy, that's to maintain within less than 1% error versus, right?
Yep, that's correct. Yeah, that was our benchmark is to have less than 1% error, and that was those were the windows that we could get 1% error within.
Okay, and to clarify, you can measure both high and low material at the same time, such as you have spalling or nicking of a part, and there's material above and below the normal surface being measured.
Yeah, exactly. So if you remember my measurement, looking at the burrs on the edges, if I had some corrosion there, some pitting, I could set that reference I set a 0 point. So if there were also pits there as well, below that 0 point, I could also, using that feature analysis tool we have, be picking up the depths and the heights at the same exact time.
And that's particularly useful on things like welds that are really complex, and a lot of times you'll have big lows as well as big highs.
Mm-hmm.
Yeah. Well, thank you. We're just about out of time. I want to thank you attendees for your attention and questions, and thank you, Dr. Eric Novak and Kramer Lindell, for your insights. Don't miss these upcoming IMTS Spark conferences. Today at 2 p.m. Eastern, enabling additive manufacturing for production via integration and connectivity. David Flynn, Senior Business Development Manager at Materialize USA, will discuss implementing the right digital tools if you are planning to set up an additive manufacturing or scale your current additive manufacturing production. Let's try to say that 3 times fast. Next Tuesday, November 24th at 12:30 p.m. Eastern, manufacturing in 2020 and beyond. Questions to ask before investing in new machine tool technology. Chairman of Mitsui Seiki USA, Scott Walker, offers a presentation for machine tool buyers in today's manufacturing environments. Also on November 24th at 2 p.m., simulation paves the way for productivity with additive manufacturing. Gene Granata, Vericut Product Manager at CG Tech, will explain how additive manufacturing simulation software can validate that planned operations and setups will work and parts are producible. Watch your email for invitations to register, or you can find more IMTS conference sessions at imts.com/spark. Thank you and goodbye for now.
Thank you, Eric.
Thank you.